Myself Dr. Deepika Saini from Lloyd Institute of Management and Technology. So, today we are back with anticonvulsant part 2. In the part 1, we have already studied about the general introduction of anticonvulsant. Apart from that, we have also studied about different type of seizures, including the partial one and the generalized one, and we have also classified anticonvulsant into different drugs categories, in which we have studied two categories. One is barbiturate and another one is hydantoin, including the structure activity relationship and synthesis of some of the important compounds. So, today let us begin with oxazolidinedione. As the name suggests, it includes one oxygen, one nitrogen, and di means 2, ons means carbonyl group. So, it includes an oxygen atom, a nitrogen and two carbonyl group, basically two ketonic groups. So, when we compare it with hydantoin, we can simply say that we have just replaced the nitrogen at position number 1 with an oxygen atom. Like, see, at this position number 1, we have NH group. We have just replaced this with an oxygen atom. And what we get? We get oxazolidinedione. So, while numbering, what we found, it is 1, 2, 3, 4 and 5. We have seen there is ketonic group, this carbonyl group at position number 2 and at position number 4. That is why they are also known as oxazolidine 2,4-dione system. So, replacement of NH group at position number 1 in the hydantoin with an oxygen atom, that produces oxazolidine 2,4-dione system. These are the some structural examples of oxazolidinedione. Again, we have just like 1, 2, 3, 4 and 5. We have again 3 possibility of substitution. One at position number 3, the nitrogen at 3, that R3, and then again we have 2 hydrogen atom at position number 5 that can be substituted and named as R5 and R5 dash. So, we have 3 substitution options. One is R3, another one is R5, another one is R5 dash. So, let us begin with the trimethadione. In case of trimethadione, as the name suggests, tri 3 metha methyl. So, we have 3 options of substitution and all are substituted with methyl substitution, methyl group. So, when we substitute R3, this nitrogen with the methyl group, these two R5 with methyl group. So, what we found? We found trimethadione. So, next is paramethadione. So, it is almost similar to methadione. The only difference is the one of the methyl ring, methyl group is substituted, is replaced by ethyl group. So, we have at position number 3, the nitrogen is substituted with again with a methyl group. Apart from that, R5 and R5 dash, they are substituted as CH3 and C2H5. In case of dimidone, here dimidone, it is almost similar to paramethadione. The only difference is here the R5 the 5th position is substituted with 2 methyl group, while the position, the 3rd position of nitrogen, that is substituted with the ethyl ring, ethyl group. So, apart from that, we have maledione also, in which a double bonded substitution is there at nitrogen, and we have CH3. We have H at position at the nitrogen, and this double bonded is found as at the substitution at position number 5. So, these are the example of oxazolidinedione. When we talk about structure activity relationship of oxazolidinedione, First of all, the position, this position number 5, the substitution at position number 5 is a main concern area. Apart from that, definitely the substitution at nitrogen, that also changes, that also affect the activity. So, must be keep in mind. First of all, we will discuss about R5 and R5 dash. The nature of substituent at carbon number 5 is very important, because there is a difference in activity, though the substitution definitely leads to anticonvulsant potential, but the potential varies in terms of activity or the type of seizure they are dealing with. Like when we talk about this substitution and that have lower alkyl group, like the examples we have seen 2-methyl group, those two, the lower alkyl group substitution that produce anti-patetymal activity, while when we take acyl group at that position, that produces anti-grandmal activity. So, there is a huge difference between the activity, though both acts as anticonvulsant agent, but the type of activity they are producing, that varies according to the number of carbon atoms at position number 5. As we have suggested, the lower one, the lower alkyl group substitution, that leads to anti-patetymal activity, while the group if we take acyl group at position number 5, that will produce anti-grandmal activity. So, when we talk about this N substitution, in this case, this substitution actually does not change the activity. So, the position, the change, any change like with the substitution as we have seen with no substitution, with methyl, with ethyl, with respect to this nitrogen, the activity does not changes. Apart from that, in the case of trimethadione was the first drug basically which was used to treat the absence seizures, that we have already discussed, the absence seizures in which patient is completely absent minded, he or she is continuously staring at a particular position. So, in that case, this triadione was the first drug that has been introduced for the treatment of absence seizures. So, this was the structure activity relationship of oxazolidinedione. The next category is succinimide. Here what we have seen? We have seen this is the position where the oxygen was also there in case of oxazolidinedione. So, the oxygen in this case we can say that particular oxygen has been replaced by CH2 group. Simply the oxazolidine, the oxygen of oxazolidinedione is being replaced by CH2 group. So, now we have again 3 positions, but again we are, when we are talking about it, it is the position 1, 2, 3, 4 and 5. At this position R1, R2 and we have R3. So, what will we say, that we have 3 options R1, R2, R3. We have 3 substitution options. The nomenclature won't be like this, we will give the shortest number to this 1, 2, 3, 4 and 5. This position, the position that contains CH2 group will get the position number 5. So, we have given R1, R2 and R3 randomly in this case. So, when we talk about it, okay, in the case of finsuccimide, what we did, we have substituted the nitrogen with the CH3 and these two have one H and one phenyl group. In case of metsuccimide, it is almost similar, the only point is again we have introduced the meth means methyl group. So, methyl group is there. In case of ethosuccimide, we have CH3, C2H5, but the nitrogen is unsubstituted. So, this is the structural examples of succimides. Now, we will talk about the structure activity relationship of succimides. When we talk about structure activity relationship of succimide, again we have two different targets. First thing is the substitution at this position, these R1 and R2 group, and the next one is the substitution at position number 2 in this case, but the nitrogen position, the only nitrogen position of succimides. So, let us discuss first the two substitution at this carbon atom. Phenyl substitution, when we do the phenyl substitution, that make it active against the electrically induced conversions. So, this is the thing that that should keep in mind. There are basically two different type of convulsions. In case of induced convulsions, we would say one is electrically induced convulsions and another one is chemically induced convulsions. So, when we treat the electrically induced convulsions, that can be treated with only when this position is substituted with phenyl ring. So, this is a phenyl, like it can be like some patient has started producing these convulsions after any electric shock or something like that. So, that is some sort of electrically induced convulsions. And when we talk about the animal models, we perform this electrically induced convulsions. In those cases, we introduce convulsions into animals, the mice basically, by giving them electric shock. So, that is a electrically induced convulsions, and that can also be produced. The convulsions can also be produced by some sort of chemicals. Some sort of chemicals means any kind of drug, like PTZ is known as the drug that is used to induce the convulsions. So, that is a chemical induced convulsions. So, when we are talking about electrically induced convulsions, that can be treated when we are treating when we have substitution of phenyl ring at the position of these two, one of them like R1 or R2, one of them if it is substituted with phenyl, then we can use it against the electrically induced convulsions. And the next part is this substitution at this nitrogen. When we study about it, this N-methylation that decrease the activity, but again against the electroshock. When we are talking about it, like if we are thinking about N-methylation, this N-methylation will decrease the activity, but against the electrically induced convulsions. But this N-methylation also increase the activity against chemically induced convulsions, as we have already discussed this type also. Like in case of chemically induced convulsions, what happen, by the effect of some chemicals that can increase this electrical signaling of neurons and can produce the epilepsy. So, in the against those chemically, like the chemically induced convulsions, we should do N-methylation. Now, the point is to whom you are treating. If you are treating electrically induced convulsions, then N-methylation is a bad idea. But when we are treating chemically induced convulsions, then N-methylation will lead to more successful and more potential candidate as anticonvulsant. And this is the synthesis of ethosuccimide. First of all, there is ethyl methyl ketone. This is treated with ethyl cyanoacetate. What is this? This is ethyl, then acetate. Acetate is CH3COO, CH2COO, because one hydrogen is replaced by the substituent, that is cyano, that is CN. So, what happened is CH2COO. This is acetate. Another point is ethyl, and we have substituted it with cyanide. So, this is cyano, this is ethyl cyanoacetate. So, we have treated ethyl methyl ketone with ethyl cyanoacetate, and by the process of condensation in the presence of piperidine, we have found ethyl 2-cyano 3-methyl 2-pentonate. So, we have found 2 pentonate. How? There is 1 and 2 because it's ethyl, 2 carbon atom, 3, 4 and this is pentonate, 1, 2, 3, 4, 2 ethyl, 1, 2, 3, 4 and 5. So, what is happening here? Ethyl, this is ethyl and 2 cyano, second position is cyano. We have started the wrong one, 1, 2, 3, 4 and 5. This is ethyl, 2 cyano, this is ethyl, at 2 position there is a cyano, at 3 position there is a methyl and 2 pentonate, because pentenoid actually, because at the 2 position there is a double bond. So, we have started, let's rewrite it to make it more clear. Let's start from here, like 1, 2, 3, 4 and 5, because it is 2 carbon atom. So, at position number first, this is ethyl, 2 cyano, okay, 3 methyl and 2 because of there is a double bond in between them, 2 pentenoid. So, this is 2 pentenoid. So, by this formation again we treat it with ethanol and there is a addition reaction with HCN and then across this double bond. So, what happens here is CN was there and apart from that CH2OH, one that contain this position has acquired a H and this position has acquired a CN. So, we have now 2 CN and C2H5 and CH3 here, C2H5 and CH3 here, C, CN and H, and CO C2H5 is as it is. It is as it is. Now, by the action of when we have did when we had did the hydrolysis of this, what happened is all the CN that has been converted into COH, because after the hydrolysis the cyano group will get converted into COOH, and apart from that this ethyl group that has also been removed and there is a hydrogen in place of that. So, by the action of hydrolysis now we have 3 COOH group, though it is an intermediate, that is an imaginary intermediate, because immediately CO2 will get released and we will found this C2H5, CH3, COH as it is, but this CO2 has been removed. So, this is CH2 and this COOH. By the heating with the ammonia, we have received this, like this carboxylic group has been converted into amide, this carboxylic group has also been converted into amide. We have formed apart from COH, now it is CONH2, CONH2. After the removal of NH3, the ring that at this position we have 1, 2, 3, 4 and 5. We have removed this nitrogen. After the removal of this nitrogen, what happens is, after removal of this NH3, now the ring this cyclization occur and there is a formation of ethosuccimide. So, let us revise it once. Let's revise it once again. Like first we have treated ethyl methyl ketone with ethyl cyanoacetate with the help of piperidine. It condenses and form ethyl 2 cyano 3 methyl 2 pentenoid. After the addition reaction occurs with respect to HCN across the double bond, H added to the cyanide one, the carbon that bears cyanide, and the CN goes to another carbon atom. When this hydrolysis occur, it has converted all the CN group into COH and also this esteric group into the COH, the carboxylic group. Further, immediately there is a release of COH and hence only those COH group, 2 COH group has been left there. After that with heating, with ammonia, these carboxylic groups has been converted into amides, and after the release of ammonia again there is cyclization and this ring get converted into ethosuccimide. So, this is the synthesis of ethosuccimide. The next category is urea and monoacylureas. This is a general example, as we can clearly see, like NH2CONH, but further we have substituted this with a benzene ring with a CHR group and C double bond O. So, when this CH2, we have CH2 here, the R is H only, this is phenacetamide, but when we have C2H5 here, then it is a phenyl ethyl and this whole part is acetyl urea. So, when we have this substitution with the hydrogen, we have no substitution, it is phenacetamide, but when there is a substitution of C2H5, then it is phenyl ethyl urea, and this is monoacylureas that also contain one of the important drug, that is carbamazepine. The structure activity of monoacylureas, we have again two categories, two target. One is this I would say this acyl urea basically, and the substituted part. So, when we talk about this NHCONH2 group, any substituent on the nitrogen of this does not alter the anticonvulsant activity. So, it does not actually affect. So, there is no substitution, we can see there is no substitution at this nitrogen, there is no substitution at this nitrogen. So, these are simply NH and NH2. The only this substitution that we are talking about now, among the aliphatic substitution, highest anticonvulsant activity is found with 7 carbon atom in the branched chain. When there are 7, up to 7, it works, but when we have further increased the number, like with the increase in number, there is increase in molecular weight, and hence there is no anticonvulsant activity, rather hypnotic activity actually predominates over the anticonvulsant activity. So, we can substitute this position also, but up to 7 carbon atoms only. After the 7 carbon atoms, it starts behaving more like hypnotic rather than anticonvulsant drug. So, in case of structure activity relationship of monoacylureas, we have studied that in case of substitution at the nitrogen of the monoacyl this acyl ureas, it will not affect the anticonvulsant activity. So, it should not be substituted. And apart from that, when we talk about the substitution with the respective this alkyl part, so it can be among the aliphatic substitution, highest convulsion anticonvulsant activity is only found when there is 7 carbon atom are present in the branch chain, but when further the number increases from the 7 carbon atom, that leads to more of the hypnotic potential rather than anticonvulsant. So, this is the synthesis of carbamazepine. First, we have taken 2-nitrobenzyl chloride. In the last class, I have told you, like we have, this is a benzene, when we substitute with this CH2, this is benzyl, this is benzyl chloride, this is 2-nitrobenzyl chloride. So, this is 2-nitrobenzyl chloride. So, in the presence of NaNH2, it will go in self alkylation, means we are using 2 moles of this 2-nitrobenzyl chloride. What will happen? This Cl is being replaced, substituted by we have this one CH2 Cl, this benzyl chloride part, another one again we have this CH2 Cl part with nitrogen. What will happen? This Cl and this hydrogen, they will get removed, the minus HCl is there. So, what will happen? And this structure is formed. Further, there is loss of HCl and this Cl and the hydrogen from this. So, this HCl, this is being removed. Now, what will happen? There is formation of double bond. After the double bond formation, there is a catalytic reduction is done. Catalytic reduction is done to convert this nitro compound, this nitro group into the amine group. So, after the catalytic reduction, these NO2 group will get converted into NH2, and after the removal of NH2 and 1 H, so the NH3 removal. Now, what is remaining here? Only the NH. NH2 and 1 hydrogen has been removed, so there is only NH. After COCl and NH3, what happened? There is CONH2 is being introduced and the carbamazepine is synthesized, is being prepared. So, let us start it again the revision of the synthesis of carbamazepine. First, we have taken 2 nitrobenzyl chloride. These 2 nitrobenzyl chloride that undergoes self alkylation with the use of NaNH2. When they get undergoes self alkylation, then there is formation of this compound. Further, the HCl is being removed, the Cl from this carbon atom and H from this carbon atom, that leads to the formation of double bond across between these 2 carbon atoms, and after formation of this compound number 3, 1, 2 and 3, after the formation of compound number 3, there is catalytic reduction that converts this NO2 group into NH2 group into the amine one, and further this NH2 and 1 hydrogen from this NH2 group, the ammonia is being removed after heating. So, there is cyclization of this compound, and further on the treatment of COCl2 with the NH3, that leads to the formation of carbamazepine. So, as we have studied in this slides in this presentation about various different categories of anticonvulsant drugs, and we have studied about succinimides, hydantoins. So, we have oxazolidinediones. So, we have came to know about different structure activity relationships of these compounds. So, just have a glimpse about these different categories. Like we have started with oxazolidinediones, and then the structure activity of oxazolidinediones, where we have studied that the position of this 5th carbon atom, that should be substituted if we have substituted with lower alkyl group, that will produce the anti-pentatemal, and if we introduce the acyl one, that produces anti-grandmal. And we have this one was the important, like the tridione was the first drug that was used to treat the absence seizures. Apart from that, then we have studied about the succinimides. In this succinimide, we came to know about if we have lower substitutions, if we have phenyl substitution, that will make it more active against the electrically induced. When we talk about this nitrogen, if methylation is done for the electroshock seizure, it is not a good idea, but when we talk about chemically induced convulsions, it is highly encourageable to substitute this nitrogen with the methyl group. Further, the synthesis of ethosuximide, further the urea and monoacylureas, among which carbamazepine, one of the most important drug of this category. The structure activity relationship, in which we have found that more than 7 carbon atom at this position will definitely lead to hypnotic potential rather than anticonvulsant one, and the last one, the synthesis of carbamazepine. In the next class, we will study about the remaining classes of anticonvulsant drugs. Thank you.